All right. So today we are talking about 4.7, which is applied optimization. I really love this unit, or this section rather. I think that there are so many things to think about in terms of when would you ever use calculus and why might that be important to you. And in a parallel setting, this goes sort of hand in hand with 4.1, all right, which is called related rates. And it would be a section that I would definitely spend some time on. I expect questions from 4.1. So if you haven't watched the video yet, it's okay to have questions. And I would encourage you to, ask sooner rather than later. But one thing I want to point out, in case you have not taken a look at 4.1 yet, why is my screen being funny, is that when we look at related rates, instead of having like a ddx, we're going to be looking at a ddt situations, since rates are changing over time. Okay, so 4.1, whether you've looked at it yet or not, really is all about time. How do things change over time? Now, why would I tell you that when we're not doing 4.1 today? Because 4.7 and 4.1 are both a lot of word problems, all right? So I can see through my computer screen into all of those black squares and people already being like, word problems are the worst. And I get it. I think that they're challenging. But in 4.1 and 4.7, we have both sections involving word problems. And so things I want us to start to look out for are that if you have a lot of information about time, that is probably a related rates problem. Okay. Whereas if you have things that we'll see are not really about time, but rather what do we highlight here? How do we find a maximum or a minimum of an amount? Then we're thinking that we are optimizing something. Okay, so when we see time, we're thinking related rates. When we see maximum or minimum in a word problem, we're thinking optimization. Okay, but they are two separate flavors of questions. So it would be important to make sure we know the difference between those. All right, so let's backtrack a little bit with what we know. So what we know is horizontal tangent lines. And I'm wondering if you can tell me one important thing about horizontal tangent lines. Slope is 0. Yes, I agree. Right, so we can say that the slope of a horizontal tangent line is 0. Now, if I had a curve, I wanted to draw a curve that had a horizontal tangent line, what might that look like? And if you've used the annotation feature right now, this is a great time if you want to throw a diagram on here. What does a curve that has a horizontal tangent line, like what does that look like? And you can also describe it. I love it. Could be a parabola, could be a sine wave, cosine wave. Perfect, perfect. Okay, exactly. I love it. All right. So we've got one version of what it might look like to have a horizontal tangent line. Then I think to sort of get at the same idea that other people are getting at in the chat, it could also be a situation where maybe we are at the low end of a curve, right? So this would be like a minimum, and let's see if I can do this well. Whoops. this would be a maximum, right? All right, so we have a minimum, we have a maximum, and that's where we typically have horizontal tangent lines, okay? I really like that people are bringing up sine and cosine waves because you can have a curve that has more than one, all right? And as it turns out, we're going to be taking a look at curves that for our purposes only have one, maximum or minimum, right? And so when we say, how do we find the maximum or minimum of a desired quantity? What we really want to say is, when is the slope equal to 0? And another way to say that would be, when is the derivative equal to 0? Right? So this concept that we've been talking about so much, slope equals 0, derivative equals 0, that is going to take us very far in this unit. Okay. All right. So let's unpack that a little bit more. Okay, I'm going to draw a picture here that is perhaps one that involves a maximum as well as a minimum. And so maybe that looks something like this. All right. So let's say we have some function. We'll call this f of x. And we had one point where there was a slope of 0. And we could say slope equals 0. And we had another point down here where the slope is 0. Now, how would you use slope to tell me the difference between the pink one, where the slope is 0, and the green one, where the slope is 0? I would agree. The pink is a maximum, right? And we can maybe say that the green is a minimum. But how could you tell me using slope of the function? Like, I know the slope of the function here is 0. But what about the slope on this side? Okay. So if you were to describe the slope in this region, you may say slope is positive, right, in this part right here. What would you say about this slope, like the slope of this region? Okay. And slope here we know is 0. What about slope on the other side of that minimum? It turns positive. Okay. So if you were to tell me where a maximum point is, maybe you could say the slope goes from positive to negative. Yeah, positive to negative. It has to go through 0 at some point. And when the slope goes from positive to negative, we have a maximum, right? And similarly, if we go from negative to positive, we're going to have a minimum, all right? And so that question, we're actually going to dive deep, a little bit more deeply into in 4.3 through 4.5. Okay, so this idea of, is it a maximum or is it a minimum? We're going to save that for the next few days. Okay, but I'm wondering if you can tell me if I want to find this derivative and I want to set it equal to 0, as I said over here, that's going to give me one of these 2 points, right? And for a certain curve, there might be only one, and for others, there might be more than one. And one thing for us to keep an eye out for is which maximum or minimum points fit our scenario. Okay, so that's something we want to be aware of. Which ones actually fit our scenario, whereas and make sense while others make no sense at all. Okay. And so let's leave the concept for right now. All right, this idea that we're going to be looking for slope equals 0 or where the derivative equals 0. And let's actually do a little brain dump of some useful formulas. All right. So some people, for some reason, don't really like geometry. Anybody in here a fan of geometry? I know it's hard to see if you're a fan of anything math related this early in the morning. I get it. But with geometry, some people really like geometry. I know I just said some people don't like it, but some people like it because it is very visual. You can kind of see like what you're finding, whether it be surface area, which is more like the skin of something, or volume, which is like the amount of stuff inside of something. And for right now, we're going to focus on a few formulas. All right. So thinking forward to that reference sheet, it might be a good idea to write these formulas down there. But I'm wondering if we can start with maybe some thinking about perimeter. So if I asked you to find the perimeter of any shape, what would you tell me to do? Good. Yeah. We are going to add all side lengths together. We're going to add all the side lengths together. Okay. Now there is a special formula for perimeter. What is perimeter of a circle called? Because we don't call it perimeter. Call it something else. Yeah, circumference is perimeter of a circle. We just call it a different name. All right, so circumference of a circle, what's the formula for that? Yeah, 2 pi r. Alternatively, we occasionally have pi d, like pi times the diameter. But I will say that it tends to be more useful in calculus to be using the 2 pi r. Okay, so it isn't that pi d is a bad equation, it's that we tend to measure things based on the radius rather than the diameter. Okay. All right, let's talk a little bit about area. And so in particular, area would be finding, let's go with some different shapes. Area of a rectangle. What do we have? All right, 2a plus 2b or 2l plus 2w. Yeah, that would be perimeter, right? We've shifted a little bit. Now we're talking about area. Length times width, yeah. So area of a rectangle, we typically use length times width. All right, or some people say base times height. That's okay too. All right. So let's see, area of a rectangle. How about area of a circle?
Pi r squared.
Yeah, we're gonna have pi r squared, okay? And let's do one more area. This one in particular, let's call this surface area of a cylinder. Anyone happen to know this formula?
It's like 2 pi r heights, right?
This one I think is a very long formula, and it's really easy to say, how in the world am I supposed to memorize that, right? So what Abby has put in the chat is correct, but how would you go about memorizing that? And so let's unpack this surface area real quick. And so if I look at the surface area of a cylinder, I know that there are two circles. In fact, there's a top circle and a bottom circle, right? So the top and bottom, there's each a circle. And then the sort of around the side of the can, like where there might be a label for a can, what shape is that? Like if you've ever peeled a label off of a can.
Rectangle.
Yeah, that's a rectangle, right? Or if you think about a roll of toilet paper or a roll of paper towels, when you pull the sheet off, it's actually a rectangle. And so the cylinder is actually made up of two circles and one rectangle. All right, so two circles and one rectangle. And based off of what we know, the area of a circle, we just said that was pi r squared. Right, so the term that is 2 pi r squared, that takes care of the top and the bottom of the cylinder. Plus, if I were to draw this rectangle out, that was like the label part of the can, this would be the height of the can. But you know what this is? That's actually the circumference of your cylinder. And we said that was 2 pi r. So how about we put those together? How do we find the area of that rectangle? Well, we're going to multiply the length times the width. When we multiply them, we'll get 2 pi r times h. And so if you've ever wondered how you're supposed to memorize these, 2 pi r squared comes from the two circles that make up our cylinder, plus 2 pi r h gives you the soup can label or the rectangle around the side of your cylinder. Okay. So in case you've ever wondered, that's where things come from for our surface area of a cylinder. Might make it a little bit easier to stick in your brains, but it also uses some other formulas that are useful, like area of a circle and circumference of a circle. Okay. All right, there is one last category I'd like to put up here, which is volume. And we're just going to list a few of the more common formulas. All right. So a volume of a cylinder is pi r squared h. We're going to use that one today. All right, volume of a cylinder is pi r squared h. Anyone happen to know what the volume of a cone is? Turns out the volume of a cone is very similar to the volume of the cylinder. In fact, it has the pi r squared h, but it's not a whole cone or a whole cylinder. It's actually 1/3 of a cylinder. In other words, if you take a cone and a cylinder that are the same height and the same radius, then you could put 3 cones inside of that cylinder. That's pretty cool. It's not 2, it's actually 3. So that's where we get that 1/3 from. All right, let's go with volume of a box, or sometimes we call that a rectangular prism. Any ideas for that volume formula? Good, we've got length times width times height. Some people say base times width times height, but basically when we have that volume, we should have something that is in 3 dimensions, something cubic. Okay, so I thought we would do a little bit of this brain dump just so we have a lot of our formulas accessible. But if you are going through a Desmos activity and you're like, I don't know what this formula is, it's okay to look things up, all right? But things that you end up using quite a bit, I might add to this list just so that you have a nice comprehensive situation, all right? So with that, let's jump into our practice. All right, we are going to hopefully go through 3 different questions today, depending on how long each one takes. So these are kind of longer problems, but things I want to emphasize as we go through are this. Number 1, draw the diagram. Label the diagram. That is intentionally all in capital letters because I want us to be the best artists that we can be, okay? Not in the sense that it has to be the most beautiful picture, but it has to be one that helps us unpack the meaning of the question, okay? So we're gonna draw diagrams. That's gonna be our first step, okay? Our second step is we're gonna do a formula dump. So we're going to think of all the formulas that could possibly be right, and we're going to write them down without judging ourselves. That's really hard to do. I feel like anytime I'm like, what formula should we use? I get a bunch of blank stares, and I get some folks who like immediately know what to use, and then everyone else is intimidated. But I would encourage you just to write down formulas you think might be right. It's okay to write more than you need. It's okay to go back and modify. But if you try and filter in your head, I think you just lose out on a lot of that, the bigger idea here, which is confidence building, because we are all very good mathematicians, okay? So we're gonna start with a diagram, we're gonna do a formula brain dump, and then we are gonna talk about finding the maximum or the minimum of a formula, okay? I bet we're gonna take derivatives. I bet we're going to take derivatives and set them equal to 0. That's going to be a big theme for us. We're setting them equal to 0 because maximum and minimum happen where the slope is 0. Okay. All right, so let's go ahead and get started. So it says in example 1, a rectangular garden is to be constructed using a rock wall as one side of a garden, and we have wire fencing for the other three sides. All right, so we've got a rock wall, we've got wire fencing, okay? Now, there's something sort of implied in this, which is since one side has a rock wall, we do not need wire fencing on that side. Okay, so that is implied in the question, but it might be important to write down here that this side does not need wire fencing. Okay. So a rectangular garden is to be constructed using a rock wall as one side of a garden and wire fencing for the other three sides. So we only need wire fencing for three sides. We don't need it for the fourth side. Now, given that we have 200 feet of wire fencing, determine the dimensions that would create a garden of maximum area. Okay, so right here, I'm reading through the problem. I don't see a single thing about time, but what I do see is maximum area. And because I see that phrase maximum, I'm thinking optimization. Okay. So let's start off with a diagram. All right. I can think of sort of maybe two versions of this diagram that people might have. Either way is fine, but whichever one you choose, your equations should follow from your diagram. The ways that you label your diagram should fit with the rest of your problem, okay? So it's really important that the work that you're doing builds upon itself, all right? So here is one possible diagram that we might have. You might say you have a rock wall here, and then you have wire fencing, maybe like here, here, and here. Okay. In fact, if I know I'm not going to be using fence on one side, sometimes I sort of squiggle it out. So I know that that side is not being counted in where I need the wire fencing. Okay. I would also label a diagram. So this right here is great, but I don't think that it's the most useful diagram because I haven't said this is the length, this is the width, or anything like that. Okay. Now, I'm going to go ahead and label this. It doesn't matter which one you call which. Some people like to call this the length and this the width. You could do it the other way around. That's absolutely fine. But to sort of avoid some of that, is it the length or is it the width? One thing that I like to do is if it is horizontal, I call it X. And if it is vertical, I call it Y. Okay, very boring. I don't get to use any fun letters, but in my brain, it just like makes it a little bit more logical. All right, but you can choose to label this however you want. So I'm going to call this X and I'm going to call this side Y, but I can also call this other side Y, right? Because it's a rectangle. So I know that this side is the same length as this side. All right, now it would be incorrect for me to now label this bottom side as X because I don't need any fence there. And since I don't need any fence, we probably shouldn't label it. Okay. Alternatively, some folks might say, my garden goes this way, and have something like this. And same thing, this is like the rock wall. And if I were keeping in the same vein of thought as my first diagram, I would call this one an X because it's horizontal. And I would call this one a Y because it's vertical. And so in the second diagram, I would actually have two labeled with an X and one labeled with a Y. Okay, so either diagram is fine. I think sometimes people get stuck in the beginning because they're like, well, but which way does it have to be, right? And it doesn't actually have to be any one way. You don't know yet. So that's part of that idea of just put down something, right? It doesn't have to be, right? I could also have done something like this. Maybe I go back to the first one, but my garden looks kind of like this, right? That would be fine. I would still call this Y, Y, and X. But if we look at this, because we're using variables, this first diagram and the third diagram, those are actually the same picture. Okay. And so Abby, you bring up a really good point. We don't know how long the sides are. That's okay. That's why we label them with letters, because letters can change in length. It doesn't have to be an accurate picture. So if you drew the first one, but your friend drew the second one, and your other friend drew the third one, all three of these diagrams would be valid. Okay, so that's one thing I encourage you to put aside. Don't worry so much about how big or short something is, just kind of go for the shape. That's important. And go for the labels. All right. All right, any other questions so far about the diagram? All right, so let's go to our formula brain dump. Okay. What are our thoughts? What formulas might possibly be relevant to the pictures we've drawn? Again, it's okay to have formulas that we don't end up using. That's okay. Part of the process. All right, I see something for perimeter. I see area. So let's start to write those down. Perimeter of a rectangle. All right. So perimeter of a rectangle would be all the sides added together. So if we use our x's and y's like we did here, maybe 2x plus 2y. Okay. But Jeremy, I noticed, has put in something that is like 2y plus 1x. What are our thoughts about that? Okay, so 2y plus x. All right, so I can see that we're already starting to analyze this, right? Abby and Vince, you are correct. One side is blocked by the rock wall. We don't need fencing there, right? And so if we chose this diagram or this one, we can see that we have 2y and 1x. And we know that has to equal 200 because that's how much wire fencing we have. Okay. But if you write 200 equals 2y plus 1x and you draw this picture in the middle, that wouldn't be accurate, right? How, if we use the middle picture, what equation would we use?
First or third.
Yeah, we would switch it to be 2y plus x, or 2x plus y, exactly. So just make sure whatever diagram you choose, all your formulas should represent the way that you've labeled your diagram, okay? So if we keep on with our brain dump, we have a perimeter one that seems like it's viable. Someone else mentioned area of a rectangle. And so if I think about area of primarily the ones with the green star, but in this case, it could also be the middle one. We could say that that would be x times y. Okay. Any other formulas coming to mind that maybe even potentially like the smallest chance might actually be helpful? All right, well, one that I've gotten in the past is sometimes students want to have the volume of a rectangular box or prism. Okay, and I see volume of a cylinder, which is pi r squared h, right? And so if you were doing a brain dump, you could write down as many formulas as you think might be reasonable. Why would someone think that we need a volume for a rectangular prism? Yeah, maybe that they're thinking like the garden as a three-dimensional space. That would be okay. Yeah. And if I look back at the question, maybe when I reread the question, I'm realizing they're asking for maximum area, which is a two-dimensional thing. So this is, maybe we make a note, this is 3D, not two dimension, okay? So I think very valid that maybe we need this formula, but when we go back and we read the question, since we're looking for a maximum area, maybe we don't need it for this particular question, okay? What about that cylinder one? Why might someone want to use the cylinder equation here? And Evelina, I don't want to put you on the spot, but you did suggest this, so I'm curious what your thinking was behind that. That's definitely one possibility, right? Maybe we're looking at like a gazebo, or maybe if we have a circular garden, that could also be, all right? And I think maybe in this case, for the same reasons, this is a three-dimensional, not a two-dimensional. It's okay that we wrote it down, and let's see if we need it or not, okay? All right, so this leads us to our third step. And in this case, if we go back to the question, they want us to find the maximum area, okay? So that very phrase is what I'm gonna be writing here. Finding the maximum, okay? And in particular, in this question, we are looking to find the maximum area. And if we were to translate that to ourselves, finding the maximum area actually means find the derivative of the area function. What do we do after we find the derivative of the area function? Good, set it equal to 0. And why are we setting it equal to 0? Good. Good. Because the maximum has a slope of 0. Exactly. So this word maximum here, maximum has a slope of 0. And that is such an important concept, all right? So I know that a lot of folks have really internalized this. I think this group has actually done really well with that. Now, this is the time for payback, all right? Payback in a good way. You've invested in this concept and now you get to use it in figuring out, well, how do I know that I have the most area in the garden, okay? So find the maximum area. That means for us, find the derivative of the area function, set the derivative equal to 0, and solve, all right? And so let's grab our area formula from up here. Area, we said, is x times y, or length times width, all right? So we have area equals x times y. Now, one thing that we might notice here is we have two variables. We have x and we have y. So right now, area is really a function of x and y. This right now has too many variables for us. Okay, so Calc 1 is often called single variable calculus. Okay, so Calc 1 is often called single variable calculus, where x is our variable and y is the function. Calc 3 is often multivariable. Okay, so right now, this question, a equals xy, this would be a problem that you would be able to solve in multivariable calculus in Calc 3, okay? But it turns out that we can actually use some algebra, all right? So for those folks who are like, I don't like geometry, I like algebra, here we go, all right? We can use algebra to turn too many variables into just enough variables, only one, so that we're able to solve, okay? So since this has too many variables, what we want to do is try to, we want to try and get rid of one of those variables, all right? So try to get rid of one of the variables, right? Now, if we think about what we're doing, that means we need an equation that relates x and y. Right? So we have one right here, a equals xy, but we need to find another formula that relates x and y, okay? So we go back up to our formula brain dump. Turns out we did have another formula that relates X and Y. I'm going to write that formula down right here. Okay. Which one of these letters is easier to isolate, X or Y? Good. Good choice. X, because in one step, right? This is where I sound like the cheesy sales lady. In one step, you can get X all by itself. You just have to subtract 2Y from both sides, right? So we could say that X equals 200 minus 2Y. And where did we get that equation? We did a really good job in our brain dump, okay? All right, so let's turn this multivariable calculus question into a single variable calculus question. And we're going to do that by saying everywhere we see an X, let's choose a different color. Everywhere we see an X, we're going to replace it with 200 minus 2Y. All right, that is, this X is going to become 200 minus 2Y. If you only write this I'm going to be super sad about it. You're also going to be super sad. What are you missing? Yeah, you're missing that A equals. And you know why that's such a problem? We're trying to find the derivative of the area function. And so if you don't have an A, then you're not going to get a derivative of A. So it's really important that we have A equals here, okay? One thing that I know is hard for folks is the notation. I try and be really good about our notation here. And so I just want to make sure that we are all communicating what we actually mean through that. All right. But look at this equation now. You have one variable, right? This equation, A equals 200 minus 2Y times Y, only has one variable. What is the variable here? Yeah, Y is the function, okay? And so if I want to find the derivative, the left-hand side becomes dA over what? All right, this is a good test in how good we are with our notation. How do we write the derivative of that left-hand side? Yeah, we're going to have dA dy because this bottom should match whatever variable I have left. All right, so dA dy equals, how would we take the derivative of this right-hand side? All right, tell me your ideas, but tell me what you also think is the most efficient. We could use product rule, right? I see 200 minus 2Y times Y, product rule, 100% valid. What else might I be able to do? I could use chain rule. I could distribute, and I'm going to say, let's try and distribute. Okay. And so this is where a lot of times we've, students, we've just come off this unit where we did some very complicated derivatives. And so we might try and overcomplicate the actual derivative we need to take now. But check this out. I can distribute this and I'm going to get 200y minus 2y squared. Now what rule do I need to take my derivative? I'm only going to need power rule. That's it. All right. Now let's take our derivative. Derivative of 200y. Good. 200 minus the derivative of 2y squared just gives me 4y. Very nice. Very nice. Okay. Now let me ask you a question. In the last unit, we learned about something called implicit differentiation. And so in the last unit, when we saw something like this, we would write 200y prime minus 4y prime. How come I'm not doing that here? Good, good, good. Okay, we only need implicit when taking the derivative of a function. Okay, so we only need implicit when we're taking the derivative of a function. But in our question right now, we have y as a variable. Since y is a variable, we treat it like x. We don't need implicit. Okay. And so we've taken our derivative. Turns out we only need the power rule once we do a little simplification. What do we do from here? I want the rest of this to be autopilot for us. We're looking for a maximum area. So what is our process from here? Good. We're going to set it equal to 0 and we're going to solve. And this might be the nicest equation we've seen in a very long time. I'm going to add 4y to both sides. I'm going to divide by 4. My gosh, it's even a whole number. How lucky are we? All right, so we find y to be 50. And if we go back up to our question, everything is in feet. So I'm going to go ahead and stick a feet at the end of this so I know what units I'm looking for. Okay, so y equals 50 feet. Now, it's really important that we answer the question fully. Okay, so this tells us to find the dimensions that would create a garden of maximum area. So I have the y value, right? This and this, I have the y, but now I need to find the x in order to have the dimensions. Okay. So looking at what we have so far, how can I find x? Oh my gosh, I love the way you said that. We did solve for it earlier. Okay. In fact, a lot of times this is going to happen. Somewhere along the way, you did some work that you're going to get to come back and use it to help you find that answer. And in particular, this light purple highlighted equation actually is x equals blah, blah, blah with y. So we're going to take our value for y. We're going to substitute it in for the y, and we'll be able to obtain an x value. So we can say x equals 200 minus 2y. X equals 200 minus 2 times 50. And so we get x equals 100 feet. All right. So far, we could say dimensions of our garden. We could say are 50 feet by 100 feet. But then we actually have to find that maximum area. How would we find the maximum area now that we have our dimensions? Good. Again, we have that formula, right? We said area is X times Y. We actually laid out all of the formulas we needed. We found some numbers, and then we just have to go back and substitute in all the right places. And so we will end up with 5,000. And what are our units here? Yeah, 5,000 square feet. Okay. Now it's not going to be feet because we have something in feet times something else in feet that will give us feet squared. Okay. All right, so let me get this question all on one page for us. All right, so there you are. There is our entire question. But I think most of the new learning for us is in the diagram, the brain dump, and getting rid of that extra variable. Okay, so when you are studying, think about the diagram, think about the formula brain dump, think about the maximum like setup. How do you get rid of the variables that you don't actually need? And then the rest of this, we've actually done that process over and over again, right? Find the derivative, set it equal to 0 and solve. So that part we've done, and I think we are quite good at, and we'll find that these equations are actually not too bad to take derivatives of. Yes, so the answer will be 5,000 square feet for this question. May, I'm wondering if you can rephrase your question. Why y equals what? 50 feet, okay. Because we took our derivative, we solved for y. Is that the part you mean? Oh, it does, huh? Yeah. My 7s looks like my Fs as well. So there you go. All right, so I think this is a great time for a break. It is 8:08. Let's be back at 8:23 a.m. And then we'll finish up the last hour with 2 problems. One should look very familiar if you've done the Desmos activity. And if you haven't, it'll be a very good preview for that. Okay, so I will see you folks back here in 15 minutes. All right, so here we go. Example 4. You have been asked to design a 1-liter oil can that is shaped like a right circular cylinder. And so if I were to sort of imagine what might be important here, I have a 1-liter oil can that is shaped like a right circular cylinder. And our question is, what dimensions will use the least amount of material? And so we're going to follow very similarly to what we did before, which is that we're going to start with the diagram, we're going to do a formula brain dump, and then we're going to think about what we want to maximize or minimize. Okay. Does anyone have any guesses so far whether our third step will be find the maximum or find the minimum?
Minimum.
Yeah, we're going to be looking to find a minimum in this one. Okay. Slope at a minimum, still going to be 0. Okay, so we're still going to be able to use that same find the derivative, set it equal to 0, solve, but we'll just have to do whatever our answer will be that will actually correspond to the minimum of our function. Okay, so let's start off with a diagram. Now we might think about a can in a few different ways. And so maybe we're thinking that we have sort of a regular looking can. Right, that's certainly one way for a can to be, something that looks very, very familiar. You know, if you're a Campbell's soup drinker, but coming out of that, or a can of beans or whatever it might be, but that's sort of like a regular looking can, right? Now, you could make this very tall and thin. So maybe you're like, I actually think that something like a straw-like situation might be a better design for the can, right? Ah, okay. So the right part means that the side of the can and the bottom of the can, they meet at a right angle. So in other words, it's not like this. It's not like that. Yeah. So when we say right, we mean that the side and the bottom, they meet at a right angle, okay? Which my very skinny, tall cylinder, it's a little bit harder to see, but let's imagine that there is a right angle there, okay? What might be one more alternative for a can? Yeah, maybe something that is very wide and relatively short, maybe something like a can of tuna, right? That's sort of another can design. So maybe something like this. That's a terrible diagram. Let's try this again. So maybe something like this. Okay. And that side would meet the bottom at a right angle. And so no matter what you draw your diagram to be, okay, because you don't know, right? That's what you're trying to find. You're trying to find the dimensions. So any one of these diagrams would be absolutely fine, okay? I think that maybe the last one here would be a little harder to label just because like the radius part is so small on here, but it doesn't matter if that's what you choose, then you're just gonna label things appropriately, okay? And by appropriately, we might mean something like this, where on this diagram, we could say that the radius would be here and that the height of the can would be here. Okay. Similarly, we could say the radius would be here in the second can, and this would be the height. And in the last one, we've got a very tiny radius, but a very tall height. Okay, so you do not have to draw all three. You just need to draw one and label it appropriately. All right, let's get to our formula brain dump. Start looking back at those other formulas we wrote down earlier. And let's list some off. What might potentially be useful? Don't try and limit yourself, okay? What do you think might be useful? And let's type it into the chat. Let's get a good list going.
Surface area equation.
Mm-hmm. Yep. So we could say surface area of a cylinder And what is that? 2 circles plus the rectangular part around. Okay. All right, so volume of a cylinder 2 pi r squared h. Okay. Any other things that we would like to write down in our brain dump? And again, we're not trying to limit ourselves because some of us do so much thinking inside of our head and that we sort of end up spinning our wheels because we're not sure which one is right, that we freeze and we don't put anything down. So it's almost better to put down too many things than not enough things, okay? I've had students in the past, for example, say, I'm not sure, but maybe the circumference of a circle or maybe the area of a circle, right? And so that would be valid to have those pieces of information down there, okay? We don't really decide what we need until the last step, all right? And primarily here we are finding the minimum. Now I know I don't have the question up on the screen, but what told people so quickly that they were looking for a minimum and not a maximum? Exactly, we're looking for the minimum because we're looking for the least amount of material. Now, I'm wondering if we can make this description a little bit more precise. What are we finding the minimum of?
Surface area.
Okay, so find the minimum of the surface area. What tells us that we're looking for the minimum of the surface area? Because it doesn't say in the question, find the minimum surface area, right? Good, good, good. We're looking for the amount of material. And we have a can, which means that we're filling this in particular with oil. So the inside, it doesn't say like how much oil can you fit in there. It tells us how much material we need for the surrounding shape. All right, so that's why we're looking for the minimum of surface area. And so what are we gonna do? We're gonna take the derivative of surface area of a cylinder. We're going to set that equal to 0 and we're going to solve. Okay, so same autopilot part at the end. We're going to find an equation, we're going to take a derivative, we're going to set it equal to 0, we're going to solve. All right, so let's grab that surface area equation. Make sure to write out the left-hand side. So like if you're writing an equation, you have to have something equals something else, okay? So we have surface area equals 2 pi r squared. Again, that's the top and bottom of the can, plus 2 pi r h, which is sort of the side of the can, all right? How many variables do we have in this equation? We have too many. We almost might say we have too many, right? We have 2 variables. We have r and h, all right? So we have 2 variables, which is too many, all right? So let's find a second equation to help eliminate one of the variables. All right, so we're going to find a second equation to eliminate one of the variables. what are our thoughts? Which equation might be worth grabbing from our formula brain dump? All right, so maybe the volume one, right? We had a volume equation, volume equals pi r squared h. And that equation involves r and h. Okay, so I love that Luca pointed out that the volume is 1 liter, okay? Because in the last problem we did before break where there was a fence, we knew that there were 200 feet of fence. And so we were able to replace that perimeter with 200 and actually get a number in there, okay? So we have a 1 liter oil can, all right? So in other words, the volume is 1 liter. Okay, so that is a true statement right now. 1 liter equals pi r squared h. But let me ask you a question. What units do we usually describe radius and height in? Like, what would be reasonable units to have for height and radius? Centimeters, inches, feet, right? Things that describe length. And so there's a conversion here that is particularly helpful, which is that 1 liter is actually the same as 1,000 cubic centimeters. All right, so these two equations are both mathematically correct. However, the second one will make it easier for us to measure our radius and our height. Okay, so we don't want to use the first one. We want to use the second equation. That is 1,000 equals pi r squared h. Now ask us the same question I asked us before. Which variable is easier to isolate? Yeah, we could get h by itself. We could also get r by itself, but we'd have to divide and then we'd have to take a square root. And knowing that we're headed towards derivatives, I'd rather avoid that if I can. So we are going to isolate h. That gives us h equals 1,000 over pi r squared. Okay. So we've got h equals 1,000 pi r squared. Guess what that allows us to do? Everywhere we see an h, we're going to I don't know if you can hear that, but my dog is having some dreams back here. Everywhere we see an h, we're going to put 1,000 over pi r squared. So that means in this h, we're going to put a 1,000 over pi r squared. So we'll get surface area equals 2 pi r squared plus 2 pi r times h. Now, if I look at this and I'm thinking, what rules would I need to take some derivatives? I'd be like power rule, product rule, quotient rule. That just seems unnecessary, right? So let's take a step where we simplify first, and then I bet we'll just be able to use power rule. Okay, so if we simplify, we get 2 pi r squared plus, let's see, what stays, what goes away. The pi's reduce, one of the radius reduces, and I end up with 2,000 over r. What might be an even better way to write this before I start taking derivatives? Good. So let's do that. Surface area equals 2 pi r squared plus 2000 r to the negative 1. All right. So all that work that you put in to learning how to rewrite things with their powers and all those exponential rules that I know you know, paying off big time, right? Now we were able to turn something into an equation where when we want to take the derivative, we only need power rule. And so let's take that derivative. The derivative of surface area with respect to the radius, right? So we need a dr on the bottom, is going to be 4 pi r minus 2000 r to the negative 2. Right? So we're going to use power rule. We're going to use power rule. All right. We've done most of the new stuff, all of the newer and maybe more challenging stuff. We've set up our equation, drawn our diagram, we've taken our derivative, and now we're in the home stretch. We're going to set it equal to 0. We're going to solve for r. We're going to figure out what that radius and what that height is for this can, this ideal can. Okay. So I'm going to replace the left-hand side with 0. I'm going to keep this as 4 pi r minus, but I'm going to make that second term into a fraction. Ah, good question, good question. How do we know that we are setting it to 0? All right, so let's rewind a little bit. So in this first picture we had here, right, we talked about slope being 0 at the maximum, slope being 0 at the minimum. And this is exactly the question that we're going to answer tomorrow about how do we know which one is the maximum or which one is the minimum. Okay. For these kinds of questions, I will tell you the level that I expect us to be at is mostly in the setup, that your question should have one place where the slope is equal to 0, and that will be the maximum if you're looking for a maximum, or the minimum if you're looking for a minimum. Okay, so Luca, for these questions, you don't have to worry about it, but tomorrow when we look at 4.3 and 4.5, that will really be important to know how we know if it's a maximum or a minimum. And basically it'll come down to, we'll find a point where the slope is 0. And before that, the slope will be negative. And after that, the slope will be positive. And that will give us a minimum. Okay, so that's sort of the short answer for tomorrow. All right, so let's go back down to this question. All right, well, I think we have a few choices here on how to solve this, all right? I, for one, don't really like fractions. I can work with them, but I also try and avoid them if I can. So one thing you could do here is you could multiply everything by r squared, and that will get rid of your denominator. Okay, so that's one option. Option 1 is we multiply everything by r squared. Option 2 is we're going to add that 2000 over r squared to the other side and then do some sort of cross multiplication. What would folks like to see here? Option 1, where we get rid of the fraction, or option 2, where we do more of a regular algebra kind of stuff? Okay, cool. So let's add. Right, so we added, and now we want to go ahead. I'm going to multiply the r squared. So I get 2000 equals 4 pi r cubed I'm going to divide by 4 pi. I'm going to reduce that fraction. And my last step to get r by itself is just to take the cube root of the value I got for r. Okay. This is about 5.42 centimeters once I type it into the calculator. All right. Let me just pause here for a moment. How are we feeling about the algebra to get to our answer for r? Where do we get the 1,000 from? From our 1 liter. But we don't usually, like if we're measuring liters, what do we measure R and H in? It's not really clear. So that's why we use the centimeters cubed version so that we can measure our R in centimeters and our height in centimeters. Yeah, and then we said, what's the easiest variable to isolate? I can isolate H just by dividing a bunch of stuff away, no square roots needed. So we isolated the H. And then we subbed it into our equation. Does that make sense? All right, well, let me know if it's not. All right, but since you just asked about that H formula, thank goodness we have that H formula because we want to find the dimensions of the can, meaning we have our radius, but we have to find the height. And we already found an equation. We just have to do a little bit of substitution. So H equals 1,000 over pi times r squared. Okay, and when we type that into the calculator, we should end up with approximately 10.4, nope, 10.84 centimeters. Okay. So let's go back up and make sure we've answered the question. It says, what dimensions will use the least amount of material? And it turns out that if we choose a can where the radius is half of the height, all right, so if the radius is half of the height, then you will have the optimal can design. Okay. In fact, you end up with a can where twice the radius is actually the height. Okay, so it turns out that is the shape or the dimensions that make the can have the least amount of material, but holds the most amount of stuff. Okay. Will you have to do this by hand because there's no calculators? Yeah, I do expect that you can do that sort of in your head. I'm joking. I don't expect you to do it in your head. If I asked you a question on an exam, it would be sufficient to leave your answer like this or some sort of equivalent. You don't have to worry about the simplifying. Okay. Where did the h over 1000 pi? So we have that 1000 equals pi r squared. And so if I want to get h all by itself, I'm going to divide pi r squared to both sides. So I get h equals 1000 over pi r squared. Yeah, there you go. Okay. Fun fact, I don't know how many of you out there are of adult beverage consumption age. But if you walk down the aisles in a supermarket, which is much more okay this summer than it was last summer, if you are looking in sort of the regular adult beverages that come in a can, it's like a regular looking can, right? It looks like a soda can. Your radius and height, but your 2 times the radius is actually smaller than your height. That is a regular can, okay? If you keep walking in this aisle of canned adult beverages, you will encounter a particular brand where you have the radius, you have the height, and twice the radius actually equals the height, all right? This can is not common. So even though it saves the most amount of material, meaning it uses less material than a regular can does, why do you think people don't make this shaped can more often?
Maybe packing efficiency.
Yeah, packing efficiency. Maybe it's not as attractive to consumers. So even though they could save money by using less material, not that many companies choose to use this. And I think for some of us, like myself, I'm not a particularly tall person. My hands are not particularly large. To hold something that is a little bit wider might not be as comfortable. Whereas a regular like soda can, that size seems to fit pretty well for the average sized hand, right? And so for a variety of reasons, even though this one costs less money to make, it might cost more money to pack and ship. It might cost more in terms of you won't make as many sales because people don't like the feel of this design as much. All right. So it is kind of cool when you think about like all that you can do with the calculus, where we can find things and say numerically, this is your best design. But if it doesn't fit your customer base or whatever you're trying to use it for, then it doesn't matter quite so much. All right. So this, hopefully, if you already did that Desmos activity, I might just kind of click through it again to see if you're understanding the flow of the questions a little bit more. I think they tried to ask similar things to the way I framed it here, but maybe the wording was a little different and it didn't make as much sense if you already saw it, but maybe by going back to it, it might make a little bit more sense, okay? All right, so we've got 2 more questions to take a look at. And in particular, we have this question right here, which is find 2 positive numbers such that the sum of the first number and twice the second number is 108 and the product is a maximum. All right, so that's one question. The other question is about a car rental company and thinking about how much they should charge in order to make the most money they can. All right. So let's sort of throw it out there. Who would like to take a look at example 2? Who would like to take a look at example 3? All right. All right. Well, Vince, you might be in the minority right now. But if we have time, we could definitely take a look at both of them. All right. I do get it though. I think example 2, if anyone is thinking about, starting their own business, or even if it's not their main source of income, I think it is important to think, what is the most you can charge so that you make the most amount of money? Okay. Because if you charge too little, people might think that your product is kind of not so great, right? They might say that that product seems cheap and not in a good way. You might have people who just are a little nervous, especially if you're looking at car rentals. Like, what's wrong with this car that you're renting it to me for like $2, right? But on the flip side, if you charge too much, someone might be like, why are you charging me $200 a day to rent a 1998 Honda Civic? Right? Like that might be something where it just like, it doesn't make sense. Why are you charging me so much when I could find a better deal somewhere else? And so somewhere in between these two extremes, there's this idea of a sweet spot. If you charge this amount of money, you will actually have the most income. It could be that you have more customers, you have the most amount of people who are willing to pay that amount. Okay. And so let's take a look at this scenario. Owners of a car rental company have determined that if they charge customers P dollars per day to rent a car, and they're saying that P is between 50 and 200. Okay. So it's not like they're saying maybe on the low end, if they charge $50 and they're like, for $50, you can rent a Tesla for a day. It might trap you inside and explode on you, but you can still rent it for $50 a day, right? Like we might all be a little bit worried about that. And then here's the other extreme, $200 for a pretty ratty car, right? So how much should they charge? That's going to be what we're finding out. Now, they also define that the number of cars is N, and that's the number of cars they rent per day. Okay. And it turns out they've already figured out an equation that goes with this. All right. That the number of cars per day depends on their price. In fact, if they take 100 or 1,000 minus 5 times how much they charge, that will tell them how many cars they rent per day. And so our question is, how much should they charge to maximize their revenue? Okay. Now, I will say in this case that, just to adhere to our process, we've started typically with diagrams, all right? But I think in this case, not very useful in this case, all right? Well, if it's not very useful, then maybe we jump to step number 2. And for better or for worse, the formula brain dump, I think, is really going to be where we get a lot of our information. Okay. All right. So who knows what revenue means? Okay. So revenue, income, gross income. All right. So we're thinking how much money is coming in to this company, all right? And so if we think about our income, all right, we're going to be thinking revenue is really like our income, all right? That's a helpful word to know. Revenue is like our income. And so let's say that they charged $50 per day. Okay, let's say they charged $50 per day. How many cars did they rent? Okay, so if they charge $50 per day for a car rental, then they will rent N of 50, 1,000 minus 5 times 50, which gives us 750. Okay, so we're going back to that N of P equation. Okay, well, let me ask you the second question to this. If they charge $50 per day for a car rental, what is their revenue? Because they're charging $50 per car and renting 750 cars. So 50 times 750 gives us that much income. Okay. So let's say they charge $200. Okay. If they charge 200 per day for a car rental, tell me how many cars they rent and how much their revenue. Okay, let's see. So if I think about what I said earlier, they will rent N of 200 or 1,000 minus 5 times 200, which equals 0. They will rent 0 cars. Okay. And if they rent 0 cars, then they don't make any money. All right. And so how could we turn the numbers that we did into a general equation for how much money they make in terms of P, their price? Okay, so if we wanted to find out how much they make, then we are going to have to take their number, oh no, not number, their price per car and multiply it by the number of cars they rent. And it turns out we have expressions for this. The number or the dollars per car is P, and the number of cars is N of P. Right? So let me just pause here for a moment. Are we okay with where that equation came from? We good? We not good? All right. Well, now that we have this, we know we're trying to go ahead and find something that we could take a derivative of. And in fact, we're going to be looking for a maximum. We want to make the most amount of money we can. So to us, we're going to find a maximum of revenue, which means we're going to take a derivative of our set equal to 0 and solve. All right, so we're going to take a derivative of that r, we're going to set it equal to 0, we're going to solve. And so we have our revenue equals the price times, instead of n of p, I'm going to use the equation they gave us, 1,000 minus 5p. So 1,000 minus 5p. And if I know I have to take a derivative, what would be wise to do next? Yeah, let's simplify, right? I don't want to use product rule if I don't have to. I mean, it's a good skill to have, but this is also helpful in another way, not just because we can do product rule, but actually back to Luca's question earlier, how do we know it's going to be a maximum, right? What shape is this curve? 1000p minus 5p squared. I agree. This is a parabola. More significantly, tell me which way the parabola is facing. We know our curve looks something like this. That means the one place that has a slope of 0 is going to be the maximum. Okay, so if you know what some of these fundamental graphs look like, you can actually use that to say, I know that this is going to be a maximum. By definition, I know this is a downward facing parabola. So therefore, the one place where that slope equals 0 is going to be a maximum. Okay. All right, let's take our derivative. dr dp equals 1000 minus 10p. I'm going to set that equal to 0. I'm going to say, this is even nicer than the first equation we had. I'm just going to add 10p to both sides. I divide by 10. I get p equals 100. But especially in these problems, we got to put units on what we're looking for. All right, so we found p equals 100. What does that 100 represent? Exactly. This P is how much they're charging, right? It could be that $50 for the Tesla that might blow up in your face, or the $200 for some really ratty car that's definitely seen better days, right? But it's still going to be a price. And so what we want to say here is if they charge $100 per day for the rental car, they're going to make the most amount of money. Okay. And so not everything will be, you know, a parabola or a nice linear model, but it is kind of neat to think about like how businesses actually figure out price points and things like that. Okay. So my guess is that we've all had a tiring weekend. I think that the next 2 weeks are probably the hardest 2 weeks in any summer session. There's sort of like this time, that halfway to 3/4 point where we're just a little tired. It feels like we've been working so hard, but we still have so much to go. All right, so I'll leave this example 3 for you to practice on your own time. If you'd like to work it out and then message me for an answer, I'm happy to respond to you. All right, but there are questions in quiz number 9, has questions on optimization, as well as related rates, which is the 4.1 video. Okay. So today, on this Tuesday, I will give you the gift of time, an extra 15 minutes back in your day. Small potatoes, I know, but go do with that what you will.